Let's look at some of the connections between energy and our graphs and our equations. So from an energy perspective, we can say that a simple harmonic oscillator has 1/2 Ka squared in energy, and we can say it has 1/2 mv max squared in energy. This occurs when x is at a full amplitude, and this occurs at equilibrium, but energy is conserved in this case, and so we could get rid of those halves and we could solve for Vmax. Vmax would just be dividing by m and taking the square root, and so you'd get k over m, and then you get the square root of a squared, would just be a. So from an energy perspective, we know this is true. From a force perspective, we know that F equals ma, and the maximum force in terms of its magnitude is Ka. Well, force is just Kx. The negative sign is just the direction. But the maximum force occurs at the maximum x, which is the amplitude. And we can divide by m. And so the maximum acceleration based on a force analysis is just Ka over m. Well, let's look at the equations of motion. When you look at the differential equation, it gives you x as a function of time is some a cosine omega t. If you take the derivative to get velocity, you get negative a omega sine omega t, and you get an acceleration of negative a omega squared cosine omega t. And if you look at those are just three separate trig functions, a cosine, a negative sine, and a negative cosine. There's the amplitude of the first trig function. There's the amplitude of the velocity function, which means that if sine oscillates back and forth between -1 and 1, that the velocity oscillates back and forth between negative a omega and a omega. So the maximum is a omega. Does that actually equal a omega? And of course it does, right? Omega is the square root of k over m. Look at the maximum acceleration. It's a omega squared from a calculus perspective, and down here, is that the same thing? And again, omega squared is k over m, and so these match up. So the calculus equations based on time match up with separately energy and force. You can look at the graphs as well. You can draw those nice and carefully. Beginning one would look something like that. That's our cosine curve. Then we have a negative sine curve, and again you want to match up, so not necessarily the amplitudes aren't going to be the same, because the amplitude of the position is going to be a and the amplitude of this one is going to be omega, but if we let omega equal to 1, then those three will be the same. Their periods need matched up, and so that's going to be true, that's going to be true, that's going to be true, and that's going to be true, and so you have some negative sine curve where all of those points are matched up, right? This red is the velocity. This blue is the position, and again, when it's fully stretched, it's got no velocity. When it's back to equilibrium, it's traveling at a maximum negative velocity. Fully compressed, stopped. Back to equilibrium, moving the fastest to the right. Fully stretched again, and stopped. It all makes sense, and then if you look at the acceleration is just a negative cosine curve, and it is then our dotted line. And look at that. The acceleration is going to be the biggest negative when the position is at a biggest positive. Fully stretched, accelerating the fastest to the left. No stretch, no acceleration. Fully compressed, biggest acceleration to the right. And just think of this mass on a spring. When it's fully compressed, it's going to have the biggest acceleration this way. When it's fully stretched, the acceleration is going to be this way. And hopefully it makes sense that the acceleration and the position are opposite of the same functions. Okay, so you have some connection between the graphs, the calculus, and then energy and force as well. Another thing, that I could give you a graph and you could read off information. Again, if I give you the graph, you know the amplitude is of course that value. If you found the time it took to get to this position, this is x versus t, then you could know the period. The period is the time it takes to do one cycle. One cosine is to there, one sine is to there. The periods of all three of these trig functions are the same. I could just give you a random equation. So I could say like x of t equals 5 cosine of 4t. You know, from that, you already know that the amplitude is 5 meters and omega is 4. But if you know omega, then you know the period, because the period is 2 pi over omega. That means you can write the velocity. You can find the maximum velocity. You just take the derivative and you're going to get negative 20. So the maximum velocity is negative 20, and so on. So you can get all sorts of things, you know, from this. If you know omega, you also know that omega is k over m. And so if you knew omega and k, you could find the mass, or vice versa. If you knew the mass and omega, you could then find k, and you could do all sorts of things. But all of these are connected, and you should be able to answer questions if I give you any one of these things. The last connection I want to make is, some people are like, well, how do I know whether x is a cosine or x should be a sine? And if you just think about the curves, if x is a cosine, it started at a full amplitude, which means if it's fully stretched, you're going to use a cosine. If it started and it was fully compressed, then you'd use a negative cosine. And that would start you at a negative a value. If the story goes that it starts at the origin and it's hit with a hammer to the right, well, then use a sine curve, because at t equals 0, you want it to be at 0. And if it's hit with a hammer and compressed, then use a negative sine curve. Those are really the only 4 choices. And hopefully those 4 choices make sense with the story.